Okay, so today we're going to work a little bit more with the equilibrium constant. If you remember from last time, it's a capital K, and it's related to the kinetics of the forward reaction and the kinetics of the reverse reaction, the lowercase k's. We're also going to investigate something called Q, the reaction quotient, and we're going to just introduce it today, but we'll work more with the reaction quotient as we move further in this Unit 7. Okay, so description of what reaction quotient is, and it's very much related to K, and we'll, as the unit progresses, we'll kind of get a little more in depth with that. But Kc, concentrations, Kp, pressures, Q is the same way. And we're going to look at a generic reaction here. So in this particular reaction, we have a chemical A, we have a chemical B, making chemical C and chemical D, and they have coefficients, and that's the lowercase a's, b's, c's, and d's. And they might be ones, but they may not be ones. And so to assemble a reaction quotient, and by the way, when we get into later in this section, calculating K, equilibrium constant, we'll use the same method here. We'll just, we'll have to look at each question to see how we're going to do these things. But the brackets, capital C means concentration. So I guess this would have to be a QC, and typically people do not designate these as QC or QP, even though we did talk about that up above there. But brackets means concentration, and then whatever coefficients there were in the balanced chemical equation, those are raised to the power of. If it doesn't have a concentration, or in the case of the QP, if it doesn't have a pressure, it just doesn't belong. There's no way to put those into this this formula here. Okay, so when you do the multiplications and divisions, you get an answer that will signify something for us, and we're not really ready to understand what the Q answer is going to signify until we get a little further into Unit 7. But we definitely have already defined what the K would be. Remember, if K is greater than 1, that means it proceeds more to the right, from left to right, and less from right to left. If K is less than 1, then it's the opposite idea. Yes, there's still dynamic equilibrium, meaning that there's movement in both directions, but the majority of the movement is from product to reactant. Okay, so, and again, I had mentioned that you can calculate K with that same idea. Those concentrations raised, their coefficients raised to the power of, or if it's Kp, pressures. Now this is a very nitpicky item here, but if you were to be asked to write the K expression for a chemical reaction, and you were told to write a Kc expression, you must use brackets. If you were told to write a Kp expression, you must use those partial pressure designations, the capital P's. And very nitpicky, but if you mix those up, you will not get the credit for those expressions. Okay, so I guess we have a couple different scenarios. We have homogeneous equilibrium, where everything in the chemical reaction is a gas, or everything in the chemical reaction is a liquid, or everything in the chemical reaction is a solution, has a concentration. So let me erase that. So if we were going to write a Kc expression, concentration, we need the brackets, and that 2 becomes the power of 2 there. And then, of course, there's a coefficient of 1 there, so there's a coefficient, there's a power of 1 there. We don't typically write the 1s, but that would be an expression for Kc for that particular reaction. If you were going to do Kp, no brackets this time, but you have the capital P, so that's the partial pressure of a particular gas. And again, the same coefficients becoming raised to the power of. If it's heterogeneous, well, then lots of reactions are heterogeneous, and we'll have a couple examples of those. And if you're writing a Kc expression for something heterogeneous, if it doesn't have a concentration, so like for instance, if copper metal is in the chemical reaction, it doesn't have a concentration. So when you would write the Kc expression, it would be absent of copper. You can't put that in because it has no concentration. Only items that have concentrations, brackets, could belong in there. Okay. I told you that in the last section that we'd have some kind of relationship between Kp and Kc. And this is in your equation sheet, so you don't have to memorize it. But Kp equals Kc times R, gas law constant, times temperature. Temperature has to be in Kelvin. And then this delta N idea, and we haven't run across that yet. It is moles of gas product minus moles of gas reactant. So like if we were going to look at this one here, there's 2 moles, the coefficients, 2 moles of gas product minus 1 mole of gas reactant for a grand total of 1. So in this question, if we were going to convert Kp to Kc or Kc to Kp, it would be raised to the power of 1. There are definitely times where maybe we had this reaction, 2 NO2s, gases, going to N2O4. Well, that means we have 1 product minus 2 reactants, gases, so that answer comes out to be -1. So if you raise something to the -1, basically you're just taking the inverse of it. So that can happen. Okay, so before we get into those mathematics, let's try to just assemble some expressions. So this would be typically part A of a free response question in equilibrium. So it does say here Kc or Kp on the test or in a homework question. It's probably going to tell you one or the other. It would not make any sense with this one to do a Kp expression because there's no pressures, there's no gases in there. So let's do a Kc for this one. So anything that's aqueous has a concentration. Brackets, hydronium, fluoride, and if you look, everything's a 1 to 1 to 1, so I'm not going to really have anything raised to the power of. And then HF down here, but no water. Why? Because water is a liquid. It does not have a concentration. So only aqueous items or gases. I could write a Kc for this one also. Gases can have concentrations, but I'm going to go and do a Kp for this one. Okay, so partial pressure of water raised to the power of 2 because it had a coefficient of 2. Partial pressure of hydrogen gas raised to the power of 2 because there's a coefficient of 2. And then partial pressure of oxygen raised to the power of 1. So very nitpicky, but very important to write the brackets with Kc and the partial pressure capital P's with Kp. So these ones happen to be heterogeneous reactions. So I'll give you a chance to be able to see what two of those would look like. And again, the question does say Kc or Kp. With aqueous materials in this first reaction here, it doesn't make any sense to do a Kp. Let's do a Kc. And we have brackets of copper ions. And we have concentration of hydroxide raised to the power of 2. There is nothing on the bottom of this fraction because that is a solid. Solids don't have concentrations. The next one, well, these are all gases. So that's not heterogeneous. That's a homogeneous reaction. We'll do partial pressure of NO2 to the second, partial pressure of NO to the second, and partial pressure of O2 to the first. I think we had just done that one previously. Okay, so let's jump into now some math. Here is our chemical reaction. In one experiment, the concentration of the reacting species at equilibrium are found to be the following. So at equilibrium, there's going to be reactants and products in the vessel, because reactants are becoming products, products are becoming reactants. Calculate Kc and Kp. Now, because molarities are given, we're going to start off with the Kc. So we have a product, the NO2, and there's its molarity. Don't forget that it's raised to the power of 2 because there's a 2 for that. That's the only product. And then all of our reactants, the NO has a small molarity. Let me do that again. Whoops. And it's raised to the power of 2 because that 2 right there. And then oxygen has a value of 0.127 molarity. Remember, I think it might have been the first section of Unit 7 here that I said that the K expression does not have, sorry, not the K expression, but the K answer, the equilibrium constant answer, it will not have any units involved because the units are dealing with the kinetics of the forward and the kinetics of the reverse. And if you divide those two, that kind of takes the units away. So K's have no, they're unitless. So do this work here. We have 3 sig figs, 3 sig figs, 3 sig figs. So let's try to stick with 3 significant figures with this answer. And there is our K equilibrium constant for that particular reaction. That's you're not going to see K answers that are that large typically, but that one is. Oh, we didn't finish. It also mentioned for us to solve for Kp. So remember that I said there's an equation that you can use to convert one to the other. So we have the Kc already. We have a gas law constant. We have a temperature in Kelvin. And then we need the delta N part. So we had 2 moles of gas. And then we had 2 and 1 more, 3 as a product, sorry, as a reactant. So 2 minus 3 is a minus 1. So that's going to make you take the reciprocal of that in there. That math, Kp, is that. Okay, so this time, let's write the Kc expression. I didn't do that with the last one. That would be brackets COCl2 and brackets CO and brackets Cl2. This time the Kc is already given to us. It is up to us to solve for the CO. So let's see what we got here. Let's change that back to a red. The equilibrium, if the equilibrium concentrations of Cl2 and COCl2 are the same, so it doesn't really matter what the numbers are, they're the same. So what's that going to do for us? That's going to cancel those two terms out because they're divided by each other. So that means, let's go back to our red, that the Kc was 1200, and that equals 1 divided by CO. So concentration of CO equals, whoops, that. We've got a heterogeneous equilibrium here. We've got a solid going to a solid and a gas. Calculate Kp and calculate Kc. It gives us a partial pressure. So I think it would be a little easier to just solve for Kp first. So what would be the Kp expression? Well, there's only one gas in the reaction, and it has a coefficient of 1, so power of 1. So this one is about as easy as it gets. So if you know the partial pressure of the CO2, you know the Kp. So there we go. So that's the Kp answer. And then to convert Kp and Kc, you need that. So we know 0.236 is the Kp. We don't know Kc. R value, 0.0821. Temperature, 800 Celsius, but to get it into Kelvin, you need to add 273 to that. So let's put that in there. I was almost going to put 800 in there. Okay, and then we have one gas, delta N, is one gas product minus no gas reactants for a total of 1. So I think I might just leave this one for you guys to finish, but it'd be 0.236 divided by the gas law constant and the temperature if you put it in Kelvin. Okay, so that's how you would convert the Kp into a Kc. And that might be, yeah, that's it.